Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this is about Vowpal Wabbit. Vowpal Wabbit is an open source project hosted on GitHub, which you can download here if you're interested. Okay, so I think I want to try to get across what exactly VW is as well as possible. I think the best description is it's kind of a research delivery vehicle. So there's various research that we do in machine learning, and putting that into VW has been one of my goals, because I think if you just, okay, so I ended up frustrated as a theorist at times, because I would develop algorithms that I thought were great, and maybe I was right or maybe I was wrong, but nobody was trying them. And by actually putting these algorithms into code, I can put them into a state where other people can use them, and then I can discover if I was right or wrong, or maybe something in between. Okay, so there's various things that kind of make VW different. And I wanted to just give you a sense of what those are. So one of them is that it's online by default. Almost all machine learning systems use batch-oriented solutions. So you give it a big data set, and it churns for a while, and it gives you a solution. VW is actually online. That means it's very interactive. And that makes a huge difference in terms of your productivity when you're trying to solve a problem. When I first encounter a machine learning problem, let's say the size of the data set is a gigabyte or less, I think typically by the time most systems have loaded the data, I've already done my first experiment. And within an hour, I've found all the parameters. There's actually quite a number, which I can just kind of hand tune very easily to get a very good solution, like the 95% solution. So that makes it very productive. Another thing is hashing. So VW is designed to take as input much more raw information than is typical of many open source packages. So you can input raw text, right? So this is a valid input example. It says that you should have the label 1 with these features. Okay, so there's a combination of several things that this implies. One of them is you don't have to pre-process data as much as you would for some other systems. The other thing is often because we're using hashing, it turns out that for some data sets, you can actually compress your model state a great deal via the hashing mechanism. And that can be super powerful when you start getting to very large model states. Okay, so another trick is Allreduce. So about 3 years ago, actually, Alec and I and Miro and Olivier released a paper on terascale learning. And as far as I know, actually, that is the data sets that are discussed in that paper and solved are the largest data sets that have been solved by a public algorithm. I'm kind of surprised. I would expect that after 3 years, somebody would come along with something better. But this is a very effective approach to learning across a cluster of different machines. Okay, so another one is reductions. So this is actually one of my starting points for frustration, because I had this idea that maybe I could take all the complex problems that people actually encounter in the real world and turn them into simple problems, and then solve the simple problems, and then make the simple problems, make the solution to the simple problems be a solution to the complex problem, right? It's a very natural thing that happens in computer science all the time, but it was kind of often done just kind of like 1 against all is a very common reduction that people just did all the time. But it wasn't formalized or studied. So inside of VW, we've been creating a reduction stack, which allows VW to solve a lot of different problems. This is very important if you're trying to solve your problem, because often I think you don't have a simple regression problem, or you don't have a simple classification problem. You have some sort of much more complex thing. And figuring out how to map that into what into the system is done for you by the reductions to a large extent. Okay, and then another thing is this is interactive learning, right? So people don't just do machine learning for platonic study purposes. They typically do machine learning because they want to take whatever the machine learner predicts and use that to change something about the world. Right? But when you go and change something about the world, suddenly the types of guarantees that we have from learning algorithms don't really carry over very well. Right? So if you are using machine learning to choose which news stories to display, or you're using machine learning to predict which treatment a doctor should use, or if you're using machine learning for all these different purposes, you should start thinking about the difference between causation and correlation. Typical learning, regression, classification gets at correlation, but you really want to get at causation. When you trying to get at causation, you really need to be thinking about things like exploration and how you use exploration information effectively to get a good solution. So VW has algorithms for this, unlike almost everything else. And then Hal will be talking in a couple of minutes about learning to search. And there's several others which are in VW that I don't think I should go through. Are there questions about this? Yeah?
How'd you come up with the name?
Oh, yeah. There's actually, so if you go to YouTube and you search for Killer Rabbit Monty Python, there's a great little snippet, which is a lot of fun. So there's actually three, that's one of the three things. There's also, do you know Jabberwocky? So Jabberwocky is Vorpal. And then Elmer Fudd tends to lisp his R's. And I guess, yeah, so they all kind of fit together if you think about it right. We're hunting the Vorpal rabbit. Right? Exactly what the Vorpal rabbit is was not at all clear at the beginning, and is still not at all clear, but we're hunting it. Okay. So as VW has developed, it's also grown a user base. And I'd have to say that having a user base is kind of addictive in some ways. It feels nice when your things actually get used. So there's various ways to measure this. There's a mailing list with about 400 people on it that's active. There's also a lot of companies that use VW in various ways. And I'm sure there are many more. The nature of open source, of course, is that you can't really track its use very well. Okay, so I wanted to give you an example. Let's see if I can do this. So this is, let's go here. Let's make this a bit bigger. There. Okay, so if I look at these data sets, they're about 132 megabytes compressed. This is an example that Liam Batu originally did, but I'm going to start with the raw data from RCV1, right? So this is predicting whether or not you have a business article or not. So the label is plus or minus 1, and then this is some sort of stemmed words in the actual article. I would use even raw data without stemming, but this is actually the rawest data which is available for that data set. Okay, so now I can say something like, I feed it the data set. I tell it that I want a hash with 22 bits. That's adequate. I tell it that I want maybe n-grams. I want to allow skips. Maybe the default learning rate is 0.5, 0.25 works a little bit better here. And then I can let it go. Oh, let me actually start over. Let's time this. Make it slightly larger. Okay, so now it's churning through the data. You can see that it's telling you how it's doing as it's going. And it finished. Right? So this is the squared loss right here. I can tweak things. I can say I really want you to report binary loss. So the error rate is going down. This is a progressive validation loss. This is the number of examples that is processed. That's the current prediction, and that's the current label, and that's the number of features that are associated with the example at the point of printout. And I end up with 4.5% error rate in 9 seconds, right? Yeah?
You don't distinguish type 1, excuse me, type 1 and type 2 errors? Not usually.
So you can very easily, if you care about type 1 versus type 2 errors, then the way to express that is via importance weighting. So what would happen is you would importance weight and say that if the label is 1, maybe it's very important that I predict it correctly, but if its label is -1, then maybe it's not so important. So that's just a scalar that you put into things.
And then, okay, let me just, what's the hashing thing? What is that, -b, is that?
Yeah, this is controlling the number of bits in the hash. So each of the individual words and n-grams and skip-grams are expressed with a 22-bit integer, which is used to look up a parameter.
Two different words, do they remain different, or could they be sent to the same thing?
They could be sent to the same thing.
And the algorithm, past that point, you can't distinguish them.
That's right.
Got it. Thanks.
Okay, so I already described what learning reductions do, but the key problem with learning reductions is how do you make it efficient enough to be really useful, and how do you make it natural to program? And I think that we've made quite a bit of progress here. So there was that -- binary flag that I sent. This is what -- binary calls. This is a function that you create when you want to create a reduction. So I'm trying to make it, you want to make things easy to use both from the viewpoint of somebody doing machine learning, but also from the viewpoint of somebody who's creating new learning algorithms. And this is a very natural way to create a reduction. You have a function which has a base learning algorithm, takes an example as input, you call the base learning algorithm, you threshold to ±1, and then maybe you compute a loss. And that's it, right? So this, of course, can be executed very efficiently because it's just you create a stack of different reductions inside of the system that sort of compiles down to the base learning algorithm and then takes it back up. All right, so now I'll give Hal some time.
Okay, sorry. So I've been interested in structured prediction for a while. So my background is mostly in natural language processing, where almost everything is a structured prediction problem. So what do we mean? So we're trying to make a joint collection of predictions, and we want to have some sort of joint loss. So the standard example, I think in machine learning land, is sequence labeling, which is sort of typified in language land as part of speech tagging. So we get something like Pierre Vinken, 61 years old, as our input, and we want to say that Pierre is a proper noun, Vinken is a proper noun, comma is a comma, 61 is a number, and so on. And so somehow we have this expectation that being able to label, say, the second word is going to help us label the first word, so there are correlations among the predictions. And we might also believe that the loss function that we want to minimize is some sort of conglomerate loss over the entire output sequence rather than something that decomposes nicely over little bits. So another example that you might want to do is translation. This is sort of the NLP hard problem that people like to use. And here we have sort of a much more complicated structure. In sequence labeling, there's sort of this nice one-to-one correspondence between input and output. In translation, things become more difficult. So this Japanese word becomes the full sequence of national treasure. There's all sorts of reordering and so on. And sort of importantly, it's the sort of loss that you want to minimize here is really a function of the entire output sentence, not a function of some little individual prediction within it. Okay, so lots of people have worked on structured prediction. I think the standard thing that people do is conditional random fields or variants of conditional random fields like max margin Markov networks and things like that. These things tend to be difficult to program if you're not a machine learning expert. And so one of the things that we really wanted to look at was, how can we reduce programming complexity so that normal NLP people or vision people or whatever your application domain is where you have structured problems can make some progress and use state-of-the-art machine learning techniques. And I guess one observation is that lots of people have structured prediction tasks, but they don't solve them using structured prediction techniques because it's too much of a pain. And I think that this is unfortunate, and this is sort of the situation that we want to resolve. Sort of a second desiderata is that, it has to be good, right? I can give you an easy interface to use, but if it gives you crummy accuracy, no one's going to use it anyway. We also, of course, care about training speed because the development cycle is important, and because this is going in VW, and we actually had an early version, and one of my colleagues used it, and he's like, I expected VW to be faster. And I was like, okay, well, maybe we need to go back and fix this because clearly there's this expectation. And then test speed is also important because we want our applications to be efficient. Okay, so here's a couple comparison points. So this is lines of code. So let's say that you want to sit down and write a part of speech tagger. How many lines of code do you have to write? So there's CRF SGD, which is Léon Botou's package. There's CRF++, which some people may know. There's structured SVM. These all take somewhere in the order 1,000 lines of code. And here I'm trying to exclude as much of the machine learning machinery, say the optimizer part, from the actual part that does the structured prediction. In some cases, this is a little bit difficult because they're integrated. But if you think of this as order 1,000 lines of code, that's probably reasonable. For us, it's 8 lines of code, which I will actually show you in a second. In terms of accuracy, so this is on part of speech tagging using tuned hyperparameters. Basically, the x-axis is the training time, so a minute, 10 minutes, 30 minutes. And then the y-axis is test accuracy. So if you just do classifications, so this is, I'm too lazy to write a structured prediction system because it's too much of a pain. You're very, very fast if you use VW, but you're kind of crummy. You can get another point or so improvement if you use an actual structured prediction technique with not much time, right? So this is 10 minutes. This is training on about 1 million words of data. And other sort of standard systems fall somewhere else in the curve. So this is CRF SGD. This is CRF++. This is a structured SVM with this demi DCD solver. Sorry, this is structured SVM. This is CRF++. Anyway, so I can talk more about what this means if people care. But I think the point that I'm not trying to make is that yay, we're so much better, or yay, we're so much faster. I mean, we're a little bit better, we're a little bit faster, but our programming complexity is essentially 0 in comparison. This is test speed, so this is number of tokens that you can label per second for part of speech tagging and for named entity recognition. Were the last 2 bars, which are bigger, which is good. Yeah.
What is own FTS?
So this is sort of. So the question is, what is own features? So basically, we were trying to make the comparison fair by giving every system exactly the same feature set. VW also has the ability to compute internally some features that would be specified in the file. So we typically do a bit better when we use our own features, but for fair comparison, we wanted to have the other one. And the reason why own features is slower is because it's actually computing features. Here, they're on disk, but presumably you had to compute them ahead of time. So, okay, so here's an example. I wasn't actually planning on running this, but basically it sort of follows the same framework that John had. So you give it some data. You say, I have some search task. In this case, it's sequence labeling. There are 45 labels in the Pentry Bank part of speech tagging data set. There are 45 parts of speech tags. we give some sort of interpolation rate for the way that the structured prediction works. And then this is the own feat stuff that you just asked about. So we can condition our prediction on neighboring words, and we can condition our prediction on prefixes and suffixes of the word that we're trying to label. Yeah?
So how easy is it to interface with VW?
I will answer this in 1 second. Perfect question. The question was interfacing. OK, so now I have to figure out how to use John's computer.
You want the browser?
Yes, maybe John can figure out how to use John's computer.
Can you say something about if this wasn't like a sort of a canonical NLP problem, but something off a beaten track, how easy would it be to?
I'll try to answer that. I mean, I can show you sort of. Actually, you should probably go to mine because the Python version is only in mine. Just switch John Langford to HAL 3.
See what I'm doing.
Change the URL at the top.
Okay, I'll try to teach.
OK, so I guess I'll try to answer this question. So the question is for different structured prediction problems, say not sequence labeling, how hard is it to sort of roll your own? I think the answer is we're trying to make it as easy as possible. So John had an intern this summer, Kai Wei from UIUC, who was really interested in this entity resolution task, where you get a document and you're trying to resolve different entities that appear in the document to like their Wikipedia entry or their Freebase entry or something like that, which has like sort of a very complicated graph structure. And he was able to do this relatively easily. I've been working sort of behind the scenes on these collective graph classification problems where you have some sort of graph and you're trying to make predictions about nodes and edges and stuff like that. And I think a lot of complicated problems can be reduced to sort of these graph-based classification problems. So I think it's doable, but actually one of the points of putting this out is I want to see what people will try to do with it and what they have a hard time doing, because I think that's a nice way to push progress. OK, so just to give you a sense, so this is the sequence labeling. I apologize for the C++. That's John's fault. So here is the entire sequence labeler. So we have an initialize, which sets some options. So we say, I want to condition my prediction automatically on previously made predictions. I want to use Hamming loss by default. If you don't want to use Hamming loss, you have to implement your own loss. And then for optimization reasons, we're going to tell it that we're not going to modify examples inside of our code. We don't have to do anything at the end. And so we have this structured predict function, which is basically how our thing is going to work. So we get a vector of examples. We say so this vector of examples is like the words in the sequence. So for each word in the sequence, we make a prediction. And if we want to produce output, we produce output. And then that's it. So this is sort of, I think, the most natural way you could try to write a sequence labeler. It's like go through each word in the sequence, predict the label of that word. And basically, all of the sort of the structured loss and the joint feature space over the features is happening internally automatically for you.
We need to finish.
OK, so we do need to finish. OK, so then I will not show you, but you can also do this in Python. So we made a Python VW interface, and you can write essentially the same function even easier in Python, and it works as well, but it's slower because you pay foreign function interface fees.
For the
classification problem, what does the input features look like?
Repeat the question.
Yeah, so the question is for graph classification, what do the input features look like? So, I mean, it depends on what sort of data you're using. Right now, I'm just using synthetic data. So basically, each node and each edge has like some random features on it. The sort of problem that was motivating this was one of two things. So one is either like a social networky like problem where nodes represent individuals and edges represent relationships, and then you might have personal features of the person, or on the edges you might have interaction features. Other people, so Stefan Ross, who worked with us on this, and Drew Bagnall had this nice paper on using sort of graph classification for solving image segmentation problems. And so, sort of eventually we'd like it to work there too.
I didn't quite get it. So it looked like a structured multi-class classification output, which you just do per sequence element.
Yeah.
So how do you define the dependencies on the neighboring labels?
Right. So this is what was hidden in the set options auto history. So there we're basically saying condition on the k previous predictions. And that's happening automatically for you. If you didn't do that, you'd have to automatically construct these features yourself and add them to the example data structure. Which you could do, it would just take, a couple more lines of code. Obviously, for these more complicated problems, you need to do that yourself. It's only for the very simple cases that this works for you.